Everyone to this session. The session will be called From the Emperor Lizong to Elon Musk, A History of Rockets. It's a workshop by Harmohit Singh Bindra. And he started a project called Aagasa Aagas to develop better deep space propulsion technologies. He has secured $15,000 to support his research and development efforts. With his wide range of expertise, he will be taking us through a brief history of rocket propulsion from the 13th century Chinese Navy to now SpaceX in 2020. Be sure to connect with him on LinkedIn if you have any questions or want to learn more. I'll kick it over to you.
Yeah, awesome. So, hello everyone. I hope everyone can see me, hear me, and see my screen. If there are issues, you can let me know at any point, and let's get started. And just a disclaimer before I start talking that throughout this, I'll be talking about the history of rockets, obviously, and I'll take names of a lot of people who have been influential in this field and have written books, or I will describe their achievements, and I'll also try to name some of the books. And I have tried my best to research the correct pronunciations of the names that I'm going to take today. But I do realize that I'm going to make a lot of errors, and just wanted to apologize for that in advance. My name is Harmohit Singh Bindra. I started the project Aagasa Aagas, which is building tools to enhance advanced propulsion systems that are being worked on by researchers around the world. And what do I really mean by that? I'll try to answer that question over the next hour or so. And how I will do that, I'll tell that by telling a story, a very exciting story of how rockets became what they are today. And I want to keep this super casual. So if you have any questions, please feel free to interrupt me at any point, and I'll try my best to answer. And I cannot see the chat because I'm presenting. So if I don't notice you, just make a loud noise. Okay, let's start. So what is a rocket? Does anyone have any ideas? How would you go about defining a rocket?
Roland, what do you think?
Well, I didn't want to answer because I probably know a little too much, but it's basically an engine that uses that uses the explosive excretion of gases to propel a payload forward, basically, or up, or whatever direction, the opposite direction that the gases are being expelled.
Yeah, I think that's really great. That was what I was going to talk about. But I guess like you can also say that rockets are pointy things that go up, which is not wrong. But I prefer the definition that you just gave. A rocket is something powered by a rocket engine, and a rocket engine is something that uses a stored fuel, and it expels the fuel backwards in the backwards direction to what it's traveling in. And for the purposes of this talk, for this explanation, I'll consider rockets to be a lot more general. So let's say that if you are standing on a skateboard and you have a bunch of boxes with you on the skateboard, and you take a box and you throw it backwards, then the skateboard will move forward. And why does that happen? That happens because of Newton's third law of motion, which basically says that for every force, there is an opposite and equal force in the opposite direction. So you apply a force on the box when you are throwing it in this direction, and the box applies the same force to you. That's why you end up moving in the opposite direction. This is exactly how rockets work. They have some sort of a propellant, a gas that escapes through them, and they start traveling in the opposite direction. And this skateboard, you can say that the boxes are a reaction mass, and this is a very simple example of a rocket. And rockets have been used as early as the year 1232. They were used by the Chinese military as long-range arrows, so they just treated them as something similar to a bow and arrow that just happens to travel very fast. The early Chinese rockets could go up to 25 kilometers. The Chinese Emperor Lizong, who is pictured here, loved to use them as fireworks. And in the on the right here, I have a drawing of what early Chinese rockets look like, and this image was actually taken from some of the stuff that early Chinese historians have drew in their books back then, and they have survived till now. So this was the mid 13th century, and through the 14th century, rocket technology started spreading from China to the Mongols to the Middle East to India, Korea, and as far as Europe. In the mid 14th century, the Chinese invented what is called to be the Huo Long Chusui. The name roughly translates to fire dragon out of water. It was what you can call the world's first multi-stage rocket. And what it was basically was that it was bamboo sticks, and they just stuffed the bamboo sticks with as much gunpowder as they could, and they lighted it out, and there was a big rocket booster, so a big bamboo stick with a lot of gunpowder in it. And when it ran out of fuel, when it ran out of gunpowder, it just lighted several smaller bamboo sticks with more gunpowder, and the smaller ones flew around in random directions, and that caused a lot of destruction. So it was a big military success. And during the same period of time, the French author Jean Froissart was playing around with the idea of launching rockets from a tube. So the Chinese just randomly launched rockets in whatever direction they wanted to, and this French person wanted to launch them out of tubes so they can be more accurate. Until the 16th century, different parts of the world developed different rocket innovations, including some versions of multi-stage rockets, different types of fuel, some including liquid fuel, fins and nozzles of different shapes and sizes. And an Austrian military engineer, Konrad Haas, wrote a comprehensive book describing contemporary rocket technology. And this is an image of Konrad Haas working with rockets. And it was around this time, mid 15th century, that the term rocket was actually coined. Its origins can be traced back to the Italian word rocetta, which loosely translates to a little spindle. And I guess you can see why rockets were called spindles. They kind of look alike. And now we get to a very interesting point, a very interesting and controversial point in the history of rockets, the alleged first manned rocket flight. So Evliya Çelebi was an explorer who traveled through the Ottoman Empire in the mid 17th century. He traveled a lot and wrote down whatever he saw while he was traveling, and his travel records are a good source of studying history these days. But one of his accounts says that in 1633, Istanbul, the aviator Lagari Hasan Çelebi built a 7-winged rocket that contained 140 pounds of gunpowder. He then sat in the thing and launched himself from it. He landed in the sea and then swam ashore, and someone drew a picture of him doing this. At the top, you can see a thing going up. So he just took a bunch of metal, made a tube out of it, stuffed gunpowder in it, and he literally sat on it and blew himself up. And the then king of the Ottoman Empire also awarded him for his accomplishments. But the interesting thing is that Mythbusters tried to replicate this rocket flight in episode 17 of season 7, and they came to the conclusion that the historical account does not have enough information to be accurately replicated, but they generally thought that it would have been impossible for the thing to take off at the time because they didn't have any modern alloys, they didn't have steel, so it wouldn't be strong enough to hold the explosion of the gunpowder. And well, if the writer of this account was telling the truth, or he was just exaggerating stuff, or he just completely made it up, and people in the past have a lot of incentives to just make stuff up, and that's something historians talk about all the time. I don't know what happened, and I'll let you guys decide. And so moving on, in 1650, a Polish-Lithuanian nobleman named Kazimierz Seminovich wrote a book called Artis Magnae Artillerie par Prima, which roughly translates to The Complete Art of Artillery. And that book was a modern-day equivalent of a bestseller. The book was used throughout Europe as a basic artillery manual. It contained large, detailed sections of the construction, production, and the general properties of rockets. Some significant technological advancements that the book talks about are multi-stage rockets and some very advanced designs for fins that stabilize the flight of rockets. By the late 18th century, rockets were pretty much the standard in all advanced militaries. If you didn't have rockets, well, you couldn't find. And very notably, Tipu Sultan, the ruler of Mysore in India, invested heavily in the development of rockets. He really believed that rockets provided a strategic edge in battle. His rockets could travel up to 2 kilometers, which was a significant advantage at that time, and gave the British armies a very hard time in the Anglo-Mysore War. Tipu Sultan was eventually defeated by the British, but when he was defeated, the British got access to Mysore's rocket technology, which inspired the next generation of rocket development in the 19th century. A limitation for rockets of this period was that the propellant holders were not very strong. So as I have said before, what people basically used to do, that they used to take some sort of a tube made out of bamboo or any other metal and just stuff it with gunpowder. But if they would stuff in too much gunpowder, then the tube would just explode instead of going up. And Mysore rockets were so effective because they used very strong iron tubes for holding the propellant. More propellant meant that it could burn for longer, and the rocket wouldn't explode before it reached its target. And so William Congreve, a British inventor, got his hands on the Mysore rocket technology in 1801 and started doing some research, doing some experiments. He started a development program in his lab to improve on the Mysore rockets. He ended up preparing a new propellant mixture, an even stronger iron tube to hold the propellant, and a conical nose, which made the rocket aerodynamically better. His improved version of the Mysore rocket was named the Congreve rocket because he made it, and it was used by the military starting in 1805. Congreve rockets were used throughout the Napoleonic Wars. They played a large part in them, and Congreve also wrote 3 books on rockets. But a problem with both the Mysore rockets and Congreve rockets was that they were both very inaccurate. They had a very high likelihood of deviating from their intended trajectory. The accuracy of these rockets was slightly improved by attaching sticks to their sides or center. So in this image, you can see that there's a rocket, there's a gunpowder holding container at the top, and then there's a long stick below it. The stick was there basically to give the rocket some stability so that it doesn't fly away in random directions. In 1815, the Russian military officer named Alexander Dmitrievich Zasyadko started working on gunpowder-powered rockets for military applications. He recognized that there were 2 major problems with rockets at that time. The first one was that they were very inaccurate, and the second was that firing them was a very slow process, so a soldier could only fire a rocket at a time. He solved both the problems with a single invention, so he was a very smart guy. He created what was the world's first rocket launch pad, which enabled soldiers to launch up to 6 rockets at the same time. And because the rockets traveled through tubes in the launcher, they were relatively more accurate compared to their predecessors. And Zasyatko also worked extensively to set rocket weaponry production units. His innovations led to faster, cheaper, and more reliable rocket production. And he also developed several effective military strategies involving the use of rockets. In 1819, inspired from the Russian success in building rocket launch pads, artillery captains of the Kingdom of Poland, Joseph Byrne, started experimenting with rocket launching platforms. He ended up developing a very mobile rocket platform that could be carried on horse-driven carts, and he published his research notes as Notes sur les fusées incendiaires. And a very interesting thing is that the Russian and the Polish rocket launching platforms, which were the great innovations in rockets in the 19th century, they came face to face in the Polish-Russian War of 1830. The Russians ended up winning the war, but how much their rockets contributed to them winning the war, I guess that's not a very settled matter. You can argue on their importance. Although the newer rockets launched from launch pads were more accurate than their predecessors, they did often go off course. So they required these pictured long sticks to be attached for stabilizations, and the sticks made them very, very inconvenient to move around. So in 1844, a British inventor named William Hale started working on these problems and invented rockets that spun around their axes like a bullet. So the rocket would be traveling, but it would also be spinning on its axis. So it would be going like this, and it gave it some advantages. It made the rockets more accurate. It increased the rocket's range by eliminating drag, and it also eliminated the need for sticks to be attached to the rocket. So the rockets were much easier to move around for military purposes. So taking these new rockets without sticks, a British colonel named Edward Monier Boxer built an improved version of the rocket launch pads in 1865. He built launch silos that could launch 2 rockets instead of just 1. So before, soldiers could launch 6 rockets in a go, and now they could do 12. So we saw some incremental improvements here and there in rocket technology all before the 20th century, but how much rockets improved in the since the end of the 19th century is a lot. From 1901 to 1969, we literally reached the moon. So the scale of innovation, the scale of rocket development was just massive. So I would even go as far as to say that rockets developed more from 1901 to 1969 than they did in all of human history before. So why was that? Why was this? And I believe that there were 2 reasons for this happening. The first was that starting from the early 20th century, people started studying rockets with a more rigorous scientific way. And the other reason was that there was this insane cultural fascination with space travel, and there were many science fiction authors and many leading thinkers of the time that believed that rockets were something to be considered if interplanetary travel, or even not even reaching extreme altitude, even if it was just a question of reaching extreme altitudes, then rockets were the way to go. And this really begins with the French novelist Jules Verne in 1867. He published a novel called From the Earth to the Moon, a direct route in 97 hours, 20 minutes. The protagonist of the novel built a cannon that launches them to the moon. The sequel, named Around the Moon, was published in 1873 and talks of the hero's adventures after the launch. And in my opinion, this these two books really captured everyone's attention. It was the first time someone had thought of the moon as a place, as a destination that could be reached. And it was before it used to be romanticized by love, and it looked so beautiful and stuff like that. But this was, in my opinion, this was the first time that someone had actually thought of the moon as a physical place, as somewhere that can be reached and not just an inaccessible rock hanging in the sky. And it inspired a lot of other science fiction books. One of the notable ones was H.G. Wells' War of the Worlds, which tells the story of aliens from Mars invading our planet Earth. Again, this book was very successful, and I believe this was because it was so unique. It was the first time that someone had thought of Mars as a place. Someone had thought of Mars as a world where a society could exist, where people, not people, I guess, aliens like us could exist, and they were intelligent enough to realize that there is this another place called Earth, and let's go invade it. They were smart enough to do that. These books and related books of the era, I think they really captured the imagination of everyone and transformed the moon and Mars from just astronomical objects to actual places where people wanted to go. And this cultural movement was so powerful that many scientists got inspired, and they started working on the problem of space travel. They started to figure out what it would travel to take to the moon and beyond. And that's why they started a very rigorous scientific treatment of rocket science. And it started before the 20th century in 1861, when the Scottish astronomer and mathematician William Leach gave a talk in which he suggested that rockets are a possible candidate for the technology that could lead to interplanetary travel. In 1903, the Russian high school mathematics teacher named Konstantin Tsiolkovsky got inspired by the Jules Verne novel and took the idea proposed by William Leach very seriously. He did a lot of theoretical research into rockets and published his results in a book called The Exploration of Cosmic Space by Means of Reaction Devices, which was the first serious scientific work on space travel. His work inspired a lot more theoretical and experimental work in the Soviet Union, and eventually it led to the formation of Society for Studies of Interplanetary Travel in 1924. His work introduced two main ideas that still remain relevant today. The first one was the use of liquid hydrogen and liquid oxygen as propellant for the rocket, and these two are used as propellants in modern rockets. The second one was the rocket equation, this beautiful thing that I have on the screen right here. And this is just it was just so genius to put it out there, and this is an equation that still remains relevant today. This is how rockets work, and this is a major limitation for rockets today. But what does this even mean? Let's think about it. Going back to the example of our old rocket, the very simple skateboard rocket. Let's say that there's a person on the skateboard, and the person weighs, let's say, 65 kilograms, and you put 10 of these boxes on the skateboard, and each box weighs about 10 kilograms. So you have a total of 10 boxes, so that's 100 kilograms, and then you have the 65 kilogram person, so it makes the total weight about 165 kilograms. Now, when the person throws the first box of the rocket, the first box is pushing 155 kilograms of weight on the skateboard. But when the second box gets pushed, it's only pushing 145 kgs. The third box is pushing 135 kgs, and so on. So the units of fuel that are used later have a larger impact on the rocket. And the more fuel you add, the more boxes you add on top of the skateboard, the more inefficient the last box gets. So if you have 100 boxes, the 100th box is very inefficient. If you add 200 boxes, the 200th box is very less efficient than the 100th box. And this has, and as I said, this has many implications for modern rockets. Does anyone have any ideas how this would impact modern rockets? Any guesses? Okay, so the way this works is that if I put some fuel into the rocket, I cannot basically just infinitely go on putting more fuel in a rocket if I want to go far. If I want to travel twice the distance, I cannot just put twice the fuel. It doesn't work like that, because the more fuel that I'm putting in, the more inefficient the fuel added at the end gets. So it makes up making the extra added fuel more inefficient, and I have to add a lot more fuel than just the double amount to travel double the distance. And this is a serious limitation for modern rockets. In 1912, a French aircraft designer named Robert Esnault Peltier he wrote a book on rocket theory and its potential applications in interplanetary travel. He independently obtained the rocket equation and used it to do basic calculations about what would be required for a round trip to the moon. He also proposed the use of radium decay atomic power in space. Controlled nuclear fission and fusion were not possible at the time, so this was not a fancy nuclear reactor. It was the kind of atomic power sources that are used for space missions today, actually, including the Curiosity Mars rover and the New Horizons space probe. Also in 1912, Robert Goddard, an American engineer, got inspired from the work of H.G. Wells and started working seriously on solid fuel rockets. He developed a lot of the mathematics and did a lot of experiments, and ended up redesigning the combustion chamber for rockets, arranging rockets in multiple stages, and most notably, he invented and patented the de Laval nozzle, which is again something that is used in rockets today. It greatly increases the efficiency of rockets, and he published his work in 1920 as a method of reaching extreme altitudes, which attracted worldwide attention and was both praised and ridiculed. The New York Times actually made fun of this book, saying that rockets could never work, they could never take humans to extreme altitudes and forget space travel. And during World War I, a French naval officer, Yves Le Prieur, developed air-to-air solid fuel rockets that could be launched from military aircraft. If fired from a sufficiently short distance, Le Prieur rockets were quite deadly and provided a significant advantage in air-to-air combat. A German PhD student, Hermann Oberth, decided to do his research and write his PhD dissertation on the science of rocketry. He did some fabulous work, but his thesis was then rejected by the University of Munich in 1923, which goes on to show that even in 1923, less than 50 years before Neil Armstrong landed on the moon using a rocket, the general academic community was very skeptic of rocket technology ever being able to reach higher altitudes. He then published a version of his thesis independently under the title "The Rocket into Planetary Space." Modern rocketry was kickstarted on 16th March 1926 when Robert Goddard launched the world's first liquid-fueled rocket from Auburn, Massachusetts. What was so great about this rocket? Does anyone have any ideas? So what made this rocket special is that it used a de Laval nozzle. It was the first rocket ever launched that used a de Laval nozzle. But well, what makes this nozzle special? This particular kind of a nozzle can increase the rocket propellant efficiency from 2% to 64%. That's a huge improvement. But how does a de Laval nozzle work? How does it do that, and why is it so dramatic? So a de Laval nozzle works on the principle of conservation of energy, which basically says that the total energy of a system stays the same. And in our case, it means that the energy of the rocket exhaust stays the same. It does not change. And we know that rocket exhaust is very hot, so it has a lot of heat energy, which is not very useful for us. What this nozzle does is that it cools the rocket exhaust. It cools the exhaust, and when the temperature reduces, this heat energy has to go somewhere, so it goes into the kinetic energy of the exhaust. In other words, cooling the exhaust makes it escape the rocket very fast. The energy goes into making it escape the rocket very fast, and when it's escaping very fast, it pushes harder on the rocket, making the fuel more efficient. During the late 1920s, quite a few rocket research organizations appeared worldwide. In 1927, the German car manufacturer Opel started doing research on rocket vehicles along with solid fuel rocket builders Mark Vellier and Friedrich Wilhelm Sander. In 1928, they managed to drive a rocket engine powered car, the Opel RAK.1, on the Opel Raceway in Russelheim, Germany. In 1928, Opel managed to launch a manned glider using a rocket engine. In 1927, a group of amateur rocket engineers in Germany formed the Society for Space Travel. They launched a liquid propellant rocket using oxygen and gasoline in 1931. So in this period, in mid to late 1930s, governments actually started taking rockets seriously, and they started investing a lot of money into the research and development of rocket technology. Rocketry in the Soviet Union began with amateur societies. So the Group for the Study of Reactive Propulsion, or GIRD, came up, which was headed by engineers Friedrich Sander and Sergei Korolev. From 1931 to 1937, they did a lot of experimental work and theoretical work on rocket engine design, and they eventually merged with the government-funded Gas Dynamics Laboratory, or GDL, in Leningrad. This merger gave the Russian government full control over rocket development. The very well-funded and very well-staffed government laboratories started doing their work, and they built over 100 experimental rocket engines at the time under the leadership of Valentin Klashko. Their work included many advanced concepts in rocketry, including regenerative cooling, hypergolic propellant ignition, fuel injector designs that included swirling and bipropellant mixing injectors. The amazing pace of innovation at GDL was halted when Klashko was arrested during the Stalinist purges of 1938. And at the same time, a British research program was started under the direction of Dr. Alan Crowe. Their research facility was based out of Fort Halstead in Kent. They primarily worked on unguided rocket fuel rockets that could be used as anti-aircraft weapons. In 1940, they test fired a lot of rockets in the British colony of Jamaica on a range built with the specific purpose of testing rockets. So around this period in history, we start seeing a lot of government commitment and funding towards rocket technology. And it was around this time when the German military started taking rocket technology seriously because of its possible applications because of its possible military applications. And this was when they recruited the young Werner von Braun to work on long-range weapons. And von Braun would go on to do some amazing work in rockets. So the Second World War broke out in 1939. At the start of the war, the British Navy equipped their warships with unguided surface-to-air rockets. The Soviets had their own unguided rockets, and Germany had developed rocket launchers that could launch several surface-to-surface rockets at once. The German military really believed in the potential of rockets and spent a lot of time and money on building them. They had envisioned building the world's first intercontinental ballistic missile, a rocket that could carry a huge explosive warhead from one continent to another. Their dream partially came true in 1943 when Germany started the production of V-2 rockets. The V-2 rocket could travel as far as 300 kilometers, could carry a 1,000-kilogram warhead, and if launched vertically, could carry the same 1,000-kilogram payload to an altitude of 200 kilometers. This had huge implications for space travel at the time. But because people were so busy with the war, they didn't realize it, or even if they realized it, they didn't work on it, or they didn't write on it seriously. But the V-2 had shown that rockets could take humans to space someday. The V-2 was not accurate enough to have a significant impact on the outcome of the war, but it still killed thousands of people in Europe. It was enough to show the militaries of the world how lethal a guided rocket could be. By the end of the Second World War, nuclear bombs had been invented. The destructive potential of a nuclear weapon coupled with an intercontinental ballistic missile made the world governments very interested in this technology. But making rockets is hard. And Germany, before the Second World War ended, was amazing at making rockets. So after finally defeating the German forces, the Russian, British, and American militaries, they tried their best to capture German technology and to get German personnel, including scientists, to their own countries. Russia and Britain did have some success in doing this, but the United States benefited the most. They brought many German rocket scientists to their country under Operation Paperclip, and including Werner von Braun, who had been leading the rocket development in Germany and would go on to do some more great work in space travel for the United States. And here I have an image of Werner von Braun being captured by the American forces. So von Braun and his team developed the V-2 rocket and started doing their research and development activities in the US. And the German V-2 evolved into the American Redstone rocket. The US then started using rockets to study high altitude conditions by measuring temperature, pressure, etc. And they opened up a whole new area of science, which was atmospheric sciences. So atmospheric sciences is actually pretty new. It started after the Second World War. They also used rocket engines to work on more innovative technologies like the Bell X-1, the rocket engine-powered aircraft, which was the first manned vehicle to travel at a speed greater than the speed of sound. Independently, the Soviet Union space program progressed under the leadership of Sergei Korolev. With the help of the German technicians that they brought over at the end of the Second World War, they managed to replicate the V-2 rocket and renamed it as the R-1 missile. Their design was improved upon in the R-2 and R-5 missiles. Soviet Union space programs then hit a wall because they couldn't really develop their rockets any further. So they sent the German workers home and designed a new series of rocket engines based on the inventions of Alexei Mikhailovich Isaev. These new engines formed the basis for the R-7, which was the world's first intercontinental ballistic missile. The R-1 launched the first man-made satellite into space, which was the Sputnik 1, pictured here, and it eventually took Yuri Gagarin, the first man, into space and launched some lunar and planetary probes. These events attracted attentions of both the US and the Soviet governments because rockets are so effective as weapons. So both the governments started pumping money into the research and development on the work of rockets. So R&D efforts continued, but there was an important problem in the concept of space travel that had not been solved until 1951. The problem was that if you go to space into a rocket, you also must come back. But re-entering the atmosphere generates enough heat to vaporize the entire space vehicle. So Harry Julian Allen and Alfred J. Eggers of the then National Advisory Committee for Aeronautics, or NACA, made the counterintuitive discovery that a blunt, high drag shape acts as an effective heat shield and can prevent damage while re-entering the atmosphere. This permitted safe recovery of orbital vehicles, and their discovery was initially treated as a military secret, but eventually released to the public in 1958. It made possible the heat shields of Mercury, Gemini, Apollo, and Soyuz space capsules. The NACA was rebranded as NASA in 1958, and they started working on rockets. And in 1960s, there was the Cold War heightened, and both the US and the Soviet Union had developed nuclear weapons. So the pressure on both governments to have superior technology was immense. They pumped even more money into their space programs, and which which ended up with the space race ending in 1969 when NASA landed Neil Armstrong on the moon using the Saturn V rocket. In the 1970s, NASA made 5 other lunar landings before canceling the Apollo program in 1975. The Apollo program had to be cancelled because of reductions in NASA's budget, and the government couldn't really continue pumping in so much money into the super expensive space race or the space program. And while the Soviet Union and the US were engaged in the space race, the European Space Agency developed something more sustainable. In 1973, they came up with the Ariane expendable rocket family, and these rockets dominated the satellite launch market up till the early 2000s. From 1981 to 2011, NASA ran the partially reusable space shuttle program. It was developed with the intent of reducing the cost of rockets, but the space shuttle was very limited in its capabilities when compared to the Saturn V rocket. And the space shuttles unfortunately underwent 2 disasters, the Challenger disaster and the Columbia disaster. And even except all these things, no major cost savings were achieved. In 2006, Boeing and Lockheed Martin came together to form the United Launch Alliance and offer private launches on the Atlas and Delta rockets. But these rockets couldn't carry humans, only satellites or space probes. So after the space shuttle program ended in 2011, the US lost the ability to launch humans to space. All human launches since then were carried out on Russian Soyuz rockets. Around this time, the Indian Space Research Organization started doing some work on rockets, and they came up with their first reliable rocket in 2014, which is called the GSLV. While all this stuff was happening, Elon Musk came along in 2002 and started SpaceX, thinking that rockets are too expensive. After several launch failures, SpaceX successfully put a rocket in orbit in 2008. From there on, SpaceX has done several government and several private launches, successfully reused rockets, and even launched humans to space last year, returning the human launch capability to the US. SpaceX has also created an amazing startup ecosystem and inspired a lot of innovation. And I'm sure that at this event, you can find a lot of people who are working for a private space company. So how does my project, Aagasa Aagas, fit into all of this? Every single rocket innovation that I have talked about today has to do with chemical rockets. We have rocket fuels which undergo some sort of a chemical reaction, and they escape the rocket, but they have a very low specific impulse, which basically means that they are very limited by the rocket equation in what they can do. We landed on the moon in 1969, but we haven't sent any humans to Mars yet, and it's 2020. Well, it's more than 50 years. So what's happening? Like, sure, space exploration is less well funded than in the 1960s, but I think there's a deeper reason here, and the reason is the distance. Mars is the next logical step after reaching the moon, but Mars is very far away. If the moon is one step away from us, then Mars is 140 feet away, which is very far. To reach there, we need more fuel, but adding more fuel onto chemical rockets just doesn't work because adding more fuel is limited by the rocket equation. To reach Mars, we need something more, something that is not limited by the rocket equation. Well, I guess technically speaking, everything is limited by the rocket equation, but we need something with a high specific impulse, which means that something that is less limited by the rocket equation. And this is not a new problem. Physicists recognized this problem in the early 1950s and have been working on it since then. Project Orion was aimed at developing a rocket powered by nuclear weapons. Project Nerva considered nuclear reactor powered rockets. Project Prometheus was about developing electric powered rockets. And all of these projects that I mentioned were at NASA, but researchers around the world have worked on this problem with similar or different ideas, but none of them have been successful until now. But there is a common theme that ties all of these projects together, and that is that they push out plasma of the space vehicle. So similar to how rockets push out chemical reaction mass from their rockets, these advanced propulsion concepts, they push out plasma from the space vehicle, and plasma is a state of matter. It's like solid, liquid, and gas. It's the fourth state of matter. And similar to how a de Laval nozzle vastly improves the efficiency of chemical rockets, a magnetic nozzle is an analogous concept which can greatly improve the efficiency of these advanced propulsion technologies. And therefore it is a very critical component of all advanced propulsion techniques. And that is what Aagasa Aagas is. What we are trying to do is we are trying to build the first magnetic nozzle that can work with advanced propulsion systems or existing electric propulsion systems, greatly improve their efficiency, and hopefully take us to Mars. I'm happy to answer any questions now.
Thanks so much for your presentation. It'd be great if you want to drop your email address in the chat for anyone else that wants to reach out to you after the call. And that way you can come back in and see like you had a pretty good turnout in this room. I don't know if anyone wants to turn on their cameras and say hi and ask any questions, but we've got a few minutes here until the bigger Canadian Space Apps call. Yeah, it was a great presentation.
That was amazing.
Oh, wait. There we go.
Yep, Robert, we can hear you.
Hi, I have a question. That was a good presentation. I can't pronounce your first name. I'm very sorry.
Yeah, no worries.
I was wondering if you knew anything more about the Indian rocket program and anything like what their technology track might have been, and if it was following an American engineering sort of track of engineering, like American technology, or is it using some other, or was it like all indigenously developed? So I know very little about it.
Okay, so in the early days, the Indian space program had a lot of help from the Russians. So the technology is definitely more Russian inspired than American. The first Indian man in space was Rakesh Kumar, and he was sent to space by on a Russian rocket. And when the Indian space program cut ties with Russia, they started developing their own technology, and it was much less well funded than the US. So they had to find cheap alternatives everywhere. I'm not very familiar with the technical specifics, but the GSLV rocket that I talked about today, that has 4 stages of alternating fuel. I'm not sure, I may be wrong, but I think it alternates between solid and liquid fuel, which is very different from other rockets. So yeah, and also like the Indian Space Research Organization, they had to come up with a lot of clever stuff. So, like NASA has these big things in which they transport their rocket stuff around, and everything gets made at a different place, and then they put it back together. India literally did it on bicycles. They carried their rocket parts on bicycles, and there's a very iconic image that you have made.
I think there's an awesome story in there somewhere, just because countries tend to hold their rocket technology very close and don't share it. And so seeing how you would develop your own with help initially, that would be fascinating. Anyway, thank you.
Any other questions? I learned a lot. I didn't know nearly any of that history because that is not my background. So that was really, really great. Lots of great
Well,
pictures too.
I hope this wasn't like just me giving years and names and